So the lesson that we are covering next is something called implicit differentiation. And if you're wondering why we jumped from 3.7 to 3.10 and then we're going back to 3.8 and 3.9, it's because implicit differentiation is really nicely connected to the chain rule. So what implicit differentiation is, and I've got this little blurb here to kind of explain it, a function that is explicit is the type of function that you're used to. It's something that's like y equals, and then everything else is on the other side. That's an explicit function. Like I said, it's what we see almost every time that we're dealing with a function, where you've got the y by itself, or at least you can get the y by itself. That's an explicit function. An implicit function is where everything's kind of mixed together, like this example that we have right here. You couldn't get the y by itself even if you wanted to. So this equation right here, it has a well-defined slope, but the question is, how are we going to be able to find the slope when we can't get the y by itself? Because every derivative rule that we've done so far requires us to get the y by itself. So what we do is we treat y as if it's a differentiable function of x, and then we differentiate both sides. All right, so again, treat y as a differentiable function of x and then differentiate both sides. So what happens is we end up using the chain rule. So let me walk you through nice and slowly for this equation up above. So what we're going to do is we've got this equation right here. We're going to take the derivative of both sides with respect to x. Okay, so it's very similar to in algebra when you would add 3 to both sides. Taking the derivative of both sides is something that keeps the equation balanced, so it's perfectly fine. So what we're going to do is take the derivative of each piece. So take the derivative of x cubed, so that's something that we can handle. Definitely know how to do that. The derivative of x cubed is just a 3x squared. We do that using the power rule. And then next we've got y. So we treat y as if it's kind of like a nested function. So we do just like we were doing the chain rule the last couple days. So plus, when we go to take this, start with the derivative rule. So the 3 comes out front, the y stays in place, while the power drops down to a 2. So again, we're treating the y like it's a nested function. So we leave it in place when we do the derivative rule, but then we multiply by the derivative of the nested function. So we multiply by dy by dx, which again is our notation for the derivative of the nested function. All right, so then minus, the next thing we do is we've got a product rule here. So let's treat 9x as the first function and then y as the second function. So we're going to do a little product rule off to the side here. So u, that is, actually, you know what, let's keep the whole, let's do the negative 9x. So negative 9x will be u. V is just the y. So let's see, u prime, the derivative of negative 9x, again just with respect to x, is a negative 9, nice neat linear function. So this is the part that's a little tricky. Y, since it's not a function of x, the derivative of y is dy by dx, which literally means the derivative of y with respect to x. So we plug this all in using a nice product rule. So the first times the derivative of the second, so we have negative 9x times dy by dx. And then the second times the derivative of the first, so negative 9 times y. Okay, so that finishes the product rule for this piece right here, and then equals, the derivative of 0 is just 0. All right, so that's where we're at so far. All right, so then we've got this next step here. I suppose I probably could have taken up a little bit more space with this. Then we solve for dy by dx. So picture, say you're trying to get x by itself in an equation, or you're trying to get y by itself in an equation. Here we want to figure out exactly what dy by dx is. So at the end, we want like a dy by dx equals, and then all the other stuff on the right-hand side. So what we're going to do is we're going to take all of the dy by dx's and isolate them. So like this term has a dy by dx, this term has a dy by dx. So if we're trying to solve for dy by dx, like I said, just the same as if you were trying to solve an equation for x. Anything that doesn't have a dy by dx, like these two terms, we're going to put them over on the other side and then gather these terms up together. So the 3y squared, it's attached to a dy by dx, so we leave it on the left-hand side. The negative 9x is also attached to a dy by dx, so we keep it on the left-hand side. And then these other two terms, we're going to add 9y to the right it does not have a dy by dx, so we want to move it over to the other side so we can isolate the dy by dx and then subtract the 3x squared. So minus 3x squared. All right, so the next step is the dy by dx. Since we're trying to get it by itself, we're going to factor it out on the left-hand side. So factor out a dy by dx leaves us with a 3y squared minus 9x equals 9y minus 3x squared. So the next thing that we would do is divide both sides by this quantity right here. So here's what we've got so far. And I'm going to save my simplified version. So we have the 9y minus 3x squared that was already on the right, and then we divide it by the 3y squared minus 9x when we were trying to get the dy by dx by itself. So last thing, if you notice it, great. If you don't notice it, you can leave the answer just like this, but hopefully you can see that each of them has a factor of 3, so you can divide everything by 3. So I will be left with 3y minus x squared over y squared minus 3x. And that is your final answer. That's the derivative. So you'll notice here that because this is an implicit function, it's a function of x and y, your derivative is going to be a function of x and y. You're used to just seeing x's on the right-hand side. Now they're all kind of intermingled together. So this process is the process called implicit differentiation. So let's do it again with example 1. So find dy by dx, which literally means the derivative of y with respect to x, if we're solving for the function y squared equals x. So what we do is we take the derivative of both sides with respect to x. Okay, so starting with that, and again, totally legal move to take the derivative of both sides. So the derivative of this function, again, we treat it just like the chain rule. Your outside function, your main function, is something squared. Y is being, sort of this nested function, just like we did with the chain rule. So we start with the derivative rule. The 2 comes out front. We leave the nested function in place, but since we have a nested function, we multiply by the correction factor, which is the derivative of the inside. So the derivative of y with respect to x, we literally write derivative of y with respect to x. Equals, and then on the right-hand side, this is simple. We've been doing this for weeks now. Derivative of x is just a 1. Okay, and then the last thing we want to do to get the dy by dx by itself is divide both sides by 2y. So we end up with dy by dx, the derivative of y with respect to x, is 1 over 2y. So that's our final answer. So just to show you guys, this function right here is a sideways parabola. Looks something like this. Picture exactly what y equals x squared would look like, except on its side. So this is saying that at any given point, the derivative is just 1 over 2y. So like here, when y is 0, the derivative is 1 over 0, which is undefined, and that's why you'd have this vertical tangent line right here. And the same would happen with anything. Like right here, all of the y values are positive, and this line has a positive slope. Down here, if you tried to plug in a negative y value, you would end up with a negative slope if you plugged it in there. So just to show you what the picture looks like. So just to point out when we're talking about these explicit functions versus implicit functions, this equation that we see, you wouldn't be able to graph this using any sort of explicit function, like any sort of y equals function. If you wanted to, you could combine 2 separate functions. This function right here is y equals the positive square root of x, and then this function down here is y equals the negative square root of x. So if you tried to solve for y right here, when you took the square root, you would just make sure you had a plus or minus root x, and then that's where the 2 pieces come from. So it's the union of the positive square root of x with the negative square root of x. So if we really, really wanted to, even though we can see how easy this is, we could have differentiated them both separately, and we would have ended up with the same answer. So let me show you. If we differentiate this one, the derivative of y, so the left-hand side, we write dy by dx. So we're technically always doing implicit differentiation, because when you take the derivative of the left, the derivative of y with respect to x, we just write dy by dx, and that's the notation that we've used before for the derivative anyways. So equals, remember this is technically x to the 1/2. So the power rule says that the 1/2 comes out front, and then the power on x drops down to a negative 1/2. So let's write this as 1 over 2 times the square root of x. And then this one, same thing when I take the derivative of y, I get dy by dx equals, and then my answer is going to be negative because my function is negative. This is also negative, x to the 1/2. So the 1/2 comes out front, power drops down to a negative 1/2. So I can write this as 1 over, or I guess negative 1 over 2 root x. So this, technically, I have 1 over 2, and then I have a positive root x. This I also kind of have 1 over 2 with a negative root x. So if I replaced the positive root x and the negative root x with a y, this with a y, this with a y, I would land right back at the exact same derivative that I started with. It's a little more complicated actually to do it the explicit way. Implicit is really easy once you figure out exactly how it works. It's usually a nice tool to have in our back pocket. So next one here, find the slope of the circle at a certain point. So let's get just a visual here. So that circle, x squared plus y squared equals 25, that is a circle that's centered at the origin and it's got a slope of 5. So, I'm sorry, not a slope of 5, a radius of 5. So if we go 5, 5, this would be negative 5, this would be negative 5. Who knows if these are going to be equally spaced to make a nice circle. Not terrible. Done worse. All right, so there's our circle. We want the point 3, negative 4. So that would be right about there. So we want to find the slope there. So a couple of things to point out before I even do any of the calculus at all. That looks like it's going to be a positive slope. I mean, it's definitely going to be a positive slope because I'm increasing as I move this way. So like in this quadrant, I would have positive slopes headed towards actually a vertical slope, undefined. These are all negative slopes, starting with a slope of 0 right here. This would be a slope of 0 down here. Here I have negative slopes. Right on the x-axis, this would be another vertical tangent line, an undefined slope, and these are all positive slopes right here. All right, so my slopes starting over here go from vertical, positive, 0, negative, vertical. These would be positive, because remember you're kind of going from left to right. This would be 0, and then these are negative slopes as well. All right, so just to keep an eye out for what we're looking at here. So this function right here, I want to take the derivative with respect to x of both sides. Okay, so derivative of this stuff, take the derivative of each piece separately. The derivative with respect to x of x squared, nice and easy, it's just a 2x. And then plus the derivative of y squared with respect to x. Remember, we're treating y as a nested function. So I do the derivative rule. The 2 comes out front. My power on y, the nested function, drops down to a 1. And then I multiply by the derivative of y, which is dy by dx. And then equals the derivative of 25 is 0 because 25 is a constant. So my next step, just like I've been doing up above, is to get dy by dx all by itself. So start by subtracting the 2x from both sides. So I get 2y times the quantity dy by dx equals a negative 2x, and divide both sides by 2y to get dy by dx by itself. So the derivative with respect to x, I'm going to reduce down those 2's. I get a negative x over y. So let's talk about that derivative before I even plug in the 3, negative 4, because I want to show you how it works at every single point. So at any point that you plug in around the circle, my slope is going to be negative x over y. So in the first quadrant, for instance, my x and y values are both positive. Since x and y are both positive, that's why my slope comes out negative in this quadrant. In the third quadrant, x and y are both negative, so a negative number over a negative happens to come out negative, where normally a negative over a negative comes out positive. And then in the the second and fourth quadrants, because x and y have opposite signs, negative x over positive y actually comes out positive, which is why these slopes are positive. Lastly, at this point and this point, my x value is 0. So if x is 0, that's why the slope comes out to be 0. And then at this point and this point, the y coordinate is 0, which is why my slope ends up being undefined, because I have 5 over 0, or negative 5 over 0. So just to point that out. Last thing, I am looking at the specific point 3, negative 4, which we said was going to be positive. So this is Leibniz notation for that. Equals, I plug in a negative 3 because it's negative x, and then over a negative 4, which reduces down to positive 3/4. So if we're looking at our visual, that seems about right. It's definitely a positive slope, but it's not a very steep one at all. All right, so let's look at just a couple more examples on the next page because we are splitting this up into 2. Okay, so example 3, show that the slope is defined at every point on this particular graph. So not only am I going to take the derivative, I've kind of got some application to do. So I'm going to take the derivative of both sides. So let's start, I'm sorry, whoops, d, not dy, just d by dx. Same thing here, d by dx. That way I don't have to write the whole function out again. So the derivative of 2y with respect to x. I take the normal derivative. The derivative of 2 times something would just be 2, but since I have y as a nested function, I have to multiply by the correction factor, which in this whole section is always going to be dy by dx, equals the derivative of x squared is just a nice neat 2x. It doesn't have anything to do with y, so I don't have to worry about the chain rule. And then plus, here I have the sign of y. So y is a nested function. I've got to do the chain rule. The derivative of sine is cosine. I leave the nested function in place and then multiply by the derivative of the nested function. That's the correction factor. So just like I did before, I want to get the dy by dx's over to the left-hand side. So when I subtract that term, here's what I'm looking at. Okay, and then kind of in one step, I would factor out this dy by dx, and then I could divide both sides by 2 minus cosine. So like I said, I'm just going to kind of talk through those 2 steps, combine them into one. So I would have factored out the dy by dx, leaving me with the 2 minus cosine, and then I would divide both sides by the 2 minus cosine. So this is my derivative. It's part of what I'm looking for. It's not all of what I'm looking for. To show that the slope is defined at every point, I want you to consider how a slope could not be defined. The only way that a slope is not defined is if the denominator is 0. So let's talk about this denominator. 2 minus cosine y, we want to know when that is equal to 0. Okay, well, if I add cosine to both sides, that would be when cosine is equal to 2. Okay, think about that. I know we don't love the unit circle, I know we don't love trig, but we know enough about cosine to know that it goes up to a high value of 1, down to a low value of -1, and then just keeps repeating the process. It's never, ever, ever going to reach a value of 2. So there's no solution for that equation. If there's no solution for this equation, there's never going to be a point where that value is undefined. So just doing that little bit of work kind of answers the question for us. All right, 2 more. Let's do 4 and 5. So find the tangent line and the normal line to this ellipse at that point. So take the derivative of both sides. Okay, so derivative of x squared, just a nice neat 2x. This is going to require the product rule. So minus, so the first function is x, then the derivative of y is dy by dx, plus the second function is y, and then the derivative of negative x is just a -1. So let's make that negative. And then equals the derivative of 7 is 0. Oh, I'm sorry, I missed one term there, the y squared. Derivative of y squared. So then plus, we do the chain rule. Derivative of x squared would be a 2x, but I leave the y in place. And since I have a nested function, I multiply by dy by dx, and then the derivative of 7 is 0. All right, so combine up. I want these 2 terms to stay on the left-hand side. I like to put the positive term first, so I'm going to kind of reorder them. And then these other 2 terms, this negative y, I'm going to add it to both sides, so it becomes a positive y over here. And this 2x, I'm going to subtract it from both sides, so I have a negative 2x over here. Again, I'm going to kind of combine a couple steps here. Factor out the dy by dx, that leaves me with 2y minus x, and then I will divide both sides by that quantity. Okay, so that's my derivative. What I'm looking for is the tangent line and the normal line. So we'll recap in just a moment what the normal line means. Now here's the beauty of the tangent line. Not only did they give us the x value, they actually gave us the y value as well, so we don't have to work for that. Normally we have to plug it into the original function and then figure out what the y value is. So freebie. Got the y value already. So now we need to plug them both into this equation to get the slope. So if we want to know the derivative at the point -1, 2, I plug in the -1 for x, I plug in the 2 for y. So I get 2 and then minus 2 times -1 over 2 times 2 minus negative 1. So 2 minus a negative 2, I get 4 over, and then this ends up being 5. So that is the slope. So for my tangent line, we'll start with this. So y minus, and then I got the y value for free, that's 2, equals the slope that I just came up with at that point is 4/5, and then x minus the x value of negative 1. So that's my tangent line. Normal line still goes through the exact same point. The only difference between the normal line is that after they connect at this point, the normal line has a perpendicular slope. So same y value. Perpendicular slope would be the opposite reciprocal of 4/5, so a negative 5/4, and then you leave the x plus 1 right there. All right, so I think, you know what, we're going to call it right there. We'll take on example 5 starting with the next lesson.